Well, good evening, all. In today's session, we are going to talk about the CPU data path, which is the CPU actual implementation that we are going to discuss. So, in this agenda, we are going to talk about the central processors design issue. That is the central processors and control and data flow, and the data path design and implementation using the logic gates, and how the data flows from your program counter to your the memory, based on the execution cycles which we discussed in previous lectures. And then we talk about the single cycle and the multi-cycle data paths. So to cover these chapters, the topics, you can go through the first textbook, which is mentioned in a computer organization and design in chapter 4.3, which covers the building the data paths. So comes to the central processor or control and data flow. If you look into this in our previous lectures, we tried to cover the computer arithmetic, and in this computer arithmetic, we have covered the signed numbers and unsigned numbers, and the floating point representation using IEEE the format, the IEEE format, and then based on that to design the ALU, we use the logic gates to design these. We use the logic gates. The logic gates are your OR gate, your AND gate, your exclusive OR gate, and your NOT gates. These gates we used, and we tried to design the ALU. So in this central processor control and data flow, we just find out the microarchitecture level in the computer organization and the processor organization, that is in terms of data path, control, and the register file, as well as the logic circuits, including the clocking methodologies and the sequential circuits such as latches. So let me just recall and give the review of the things which we discussed in previous classes. The first one is, if you consider the computers architecture and the semantic diagram of your modern Newman processors, we have seen that there is one CPU and the memory unit and your input output subsystems. So these three units, they are interconnected with the buses we call the address buses, data bus, and your control buses. These buses are used to connect the processor to memory, processor to your input output devices, and input output devices to your memory. So in this, the figure, you can see that in this diagram, you can see that the organization of a modern Van Neumann process. That note that the CPU memory bus system, CPU, your the memory subsystem, and your input output subsystem. These are connected by the address bus, your data bus, and your control bus. So the fact that these are the parallel buses, which is denoted by the slashes here, that means these buses are connected in parallel only. So that's why we use these slashes. So it shows that these buses are connected in parallel. So in this, it is, we are going to talk about this processor design part only in this case, processor design part. So when we talk about this processor design, then it is worthwhile to further, talk about the components of this processor. So what are the components that this processor consists? So one we call the processor, or one we call the CPU, central processing unit, is the active part of your computer, which does all the work of data manipulation and decision making. And the second component of this processor we call the data path. The data path. So this data path is the hardware that performs all the required operations. For example, if you take the example of your ALU, arithmetic and logic unit operations, or your register, and some the internal buses. It uses some the internal bus. And the third one is the third component of this part is your control. The control part. So this control is the hardware again that tells the data path that what to do in terms of switching, operations, the operation selection, and the data movement between ALU components, etc. So the processor represented here, this processor, which is organized in a different way in this fashion. So the entire unit of this processor, inside this processor, it is having the control unit as said, your ALU, and your the registers. So how these internally connected, that we can see inside the schematic diagram of this processor. So there we can observe that the ALU performs the arithmetic and logic unit. It performs the input output operations on data which is stored in the registers. It performs the input output operations on data which is stored in the registers, right? And while the control unit, the control unit sends the control signals or receives the control signals with respect to the data. It sends the control signals, or they receive the control signals with respect to the data in conjunction with this register files. So in millions of instructions in MIPS, the instruction set architecture determines many aspects of the processor implementation. So for example, the implementation strategies and goals affect the clock rate and the per instructions. So these implementation constraints cause the parameters of your components. So while to performing any of the operations, in our previous discussion, we have seen, based on the performance of this, we have seen how the performance of your computer is determined. So the performance of your computer determined by three key factors that we have seen in the previous lecture. One is based on your instruction count, how many instructions are there in a program, and the clock cycle time, how much clock cycles taken by these instructions, and then clock cycle per instruction, that is the clock cycle per instruction. Based on this, we have calculated the performance of your computer. So the implementation of the processor that determines both the clock cycle time, the implementation of this, the processor that determines this clock cycle time and the number of clocks per instruction. Number of clocks per instruction. So this part will be determined by the processor. So then, we construct the data path and control unit for two different implementations of your millions of instructions per second. We try to construct the data path for this set. So to construct this data path to implement this MIPS in the basic implementation part, so we will examine an implementation that includes a subset of your core MIPS, millions of instruction per second instruction set, or we call the instruction set the architecture. So that is, what are the subset of the core subset of this the MIPS ISA means. One, the memory reference instruction. We cover in this the implementation. We follow the memory reference instructions. So what are the memory reference instructions? So that we have find these memory reference instructions, that is your load, the word is your 16-bit, right? So 32-bit. So load word and your another instruction, your store, load and store word, which we covered in the instruction set architecture. And another core subset of your MIPS, the instruction set is, we try to cover the arithmetic and logic instructions. Arithmetic and your logic instructions. So what are the arithmetic and logic instructions? We cover very few here, that is your addition, subtraction, and your logic instructions like AND instruction, your OR instruction, and your the shift instructions. And the third part is in this implementation, we cover the instruction branches or branch instructions. We call branch instructions. Branch instructions. So we covered the branch instructions like branch equal, or we can write it as the branch equal, and your jump instructions. You can write it as your J. Jump instructions, which we add at the last. So this subset does not include all the integer instructions. These subsets does not include all the integer instructions. For example, your shift instruction, or your multiply instruction, or and your the division instructions. Okay, so these are missing, and nor does it include any floating point instructions. So we will be examining an implementation that include the subset of MIPS. So the remaining operations like integer operations, shift, multiplication, division, we are ignoring, and at the same time we are ignoring the floating point instructions also. Floating point instructions also. So, however, we try to demonstrate the key principle used in creating a data path and designing the control. The implementation of the remaining instructions are, similar to what we are going to demonstrate today. So then we try to see the overview of the implementation. Overview of the implementation. So in this, in the overview, the core MIPS, the core millions of instruction per second MIPS instructions, which including the integer, it includes the integer, arithmetic and logic instructions, arithmetic and logic instructions. So we just look at this, the core MIPS instruction that include, one is your integer AL instruction, another one is the memory reference instruction and your branch instruction. Memory reference, and third one is the branch instructions. Branch instructions. So this, for every instruction, the first two steps are identical for any of these instructions for implementation part. The first two steps, are, the common, or we say identical. What are those? The first one is send the program counter to the memory. First one is your program counter, right? Send the program counter to the memory that contains the, this program counter sends instruction to your memory. It sends the program counter to the memory that contains the code and fetch the instruction from the memory. Fetch the instruction, the output of the memory is the instruction. Fetch the instruction from the memory. And second one is, in this implementation, read one or two registers, because as we observed in previous examples, that if you have the code operation like R1 is equal to your R2 plus your R3, then we write this instruction, write this operation in the instruction that it is a addition operation. So we use the add, then your R1, your R2, and your R3. So from here, it is clear that read one or two registers using fields of the instruction to select the registers to read, right? So for the load word instruction, we need to read only one register in this case. Second step, read one or two registers. But for suppose we have an instruction like, load word, for that it use only or it reads, we need to read only one register here in load word type. But most of other instructions requires reading two instructions, like it may be add, it may be your subtraction, it may be your AND logic operation, it may be your OR logic operation. They must read the two registers like R2 and R3, and then the result will go and load into your R1. So in loading one, only one register will be read, but for all other operations, two registers will be required. And this is an example which we saw in our the instruction implementation part also. So after these two steps, the one is sending TC signal to your memory to fetch the instruction, and then read the registers, then the action required to complete the instruction depend on the instruction class. Depend on the instruction class. So what are the different instruction class are they? So for each of the three instruction classes, so that is what we are saying: class 1, class 2, and class 3. These instruction classes. Okay, so the action we should require to complete these the instructions that depending upon these instruction class. So for each of these three instruction classes, like memory reference or arithmetic logic and your branches, the actions are largely the same, independent of the extra instruction. So the simplicity and regularity of the MIPS instruction set simplifies the implementation by making the execution of many of the instruction classes similar only. So for example, if you take all the instruction classes except the jump, all the instruction classes, it may be your what you call the memory reference, or your the register, sorry, arithmetic and logic, and your branch instruction, except the jump instruction, suppose. Then use the arithmetic logic unit. We use the ALU unit. We use the ALU unit after reading the registers, and the memory reference instructions use the ALU for an address calculation that we have seen in the 5-stage implementation of your instruction. Address calculation will be done, and the arithmetic logical instruction for the operation execution, and branches for comparison. So after using the ALU, the actions required to complete various instruction classes are different. So a memory reference instruction will need to access the memory either to read data for a load or write data for a store. So an arithmetic logical or your load instructions must write the data from the ALU or memory back into a register. So lastly, we can say for a branch instruction, we may need to change the instruction, the next instruction address on the comparison. Otherwise, the program counter should be incremented by your PC, incremented by 4 bytes. Because, as we see in that, we are going to talking about 32-bit instructions. So 32 bits, it requires 4 bytes, right? So let us see the symmetric diagram of your MIPS from the implementation perspective. If you say this, first, in several places you can observe in this diagram, it shows the data going to a particular unit as coming from two different sources, For example, you can see the value written into the PC can come from one of two adders. So here, we are finding two adders, right? So the input or the value which is written back to your PC, which is coming from either from this adder or from this adder or from both the adders, right? And that the data written into the register files can come from either the arithmetic and logic unit or the data memory. You can see here. So from here you can find the input for this data register file. One is input is coming from your ALU, or another one is either from your data memory or sometimes from both, right? And the second input to this ALU, the second input, this is first one, and the second input to this arithmetic and logic unit can come from a register or the immediate field of your instruction. So this is immediate field of your instruction. First one is from your register file only, but second input, it comes from either from your data or from your immediate field of your instruction. So this, so in practice, these data lines, it may be this line or this line or any of these data lines, okay. So in practice, these data lines cannot simply be wired together. So we must add a logic element. We must add some logic elements somewhere here. We must add the logic elements that choose from among the multiple sources and steers one of these sources to its destination. So this selection is commonly done with a device we call these devices we call the multiplexers. We call the multiplexers. So this, although this device might better be called as your data, sometimes multiplexer are your data selectors. So that can be done by adding these the multiplexers for the selection of your lines or selection of your different sources. So if you see the overview of this one, all the instructions start by using your program counter. All the instructions in this diagram, the implementation of your CPU, all the instructions starts from your program counter to supply the instruction address to the instruction memory. So what this program counter gives the input to the instruction memory in terms of the address of your instruction. So we have seen in our example, in our previous instruction implementation example, we have seen that there is a memory. That memory is having the instructions in the form of your zeros and one. Suppose 1 0 1 1 0 1 1 1 1 0, something like. And then every instruction 1 0 1 1 1 1 0 1 1 or 0 0 0 0 0 0 1 1 1 1 1 1. So these are the instructions they store in your memory, and every instruction is having the address, the memory address, right? That address, we have seen that address is suppose 100, then 1004, second one, or 1008, the third one, 10 or 12, fourth one, and so on. Then in the implementation, we have seen that there is a program counter PC. That PC holds the address of your next instruction which is to be executed. So initially it is empty. When the program is loaded into your memory, the first address of your first instruction will store in the PC counter, which indicates that, which gives the signal to the memory, read the instruction which is at location 100. So that is, all instructions start by using the program counter to supply the instruction address to your instruction memory, or we simply call this as the memory, this portion, right? So after the instruction is fetched, what we did, that instruction fetched and stored in the instruction register. So suppose all 1111 1111. Suppose the instruction fetch and store in the instruction register, right? So this instruction fetching will be done. Then the register operands used by the instructions are specified by field of your instruction. So we have seen the addition of your R1 and your R2 and your R3. Then when this instruction is fetched and stored into your instruction register, it is identifying the registers. So from this instruction, it is given an input to your register file. In this register file, we are going to talk about this in detail later. This register file consists of 3 registers, R1, R2, R3. So in this R1, R2, R3, R2 and R3 are the operand 1, operand 2, and the R1 is your destination. Okay, so that is your operand 1, your operand 1, your operand 2, and your destination. Okay, so from this instruction, what it says, the instruction fetch, the register operands used by an instructions are specified by fields of your instruction, like R1, your R2, and your R2, R3, and your R1. R2, R3, and R1. So the registers are identified with their numbers. Registers are identified with their numbers, right? So once the register operands have been fetched, identified, R1, R2, R3, okay? So these registers are holding the data operands, right? Okay? So once the register operands have been fetched, they can be operated on to compute a memory address, for a load, for example, for a load or your store, for loading or storing purpose. Okay, to compute or these the register operands can be fetched for to compute the arithmetic results or comparing branch results. So if the instruction is an arithmetic logic instruction, the result because from this, once these registers are identified, from R1, from R2 and R3, the operands will come, right? So the input for this ALU, the input for this ALU is the result, inputs will be given to ALU, and result of your ALU, the output of your ALU, input comes from your register file or from your immediate addressing mode. If your immediate addressing mode is there, immediate value come. Or if in our case, both the operands are from your register only. So that is your R3, second operand is here, first operand is R2. This gives the input, gives an input to your ALU, and the output of your ALU must be written to a register only. It must be written to a register only. So that is the data, the output is in the form of data that is going to write into the register only, write into the register only. So if the operation is load or store, the ALU result is this. If this operation here, if it is load or store instruction which we used, load or the store, the operation, suppose, then this the ALU result is used as the address to either store a value from the register or load a value from memory into the register. Load a value from memory into the register. So the result from the ALU or memory is written back into the register. They written back into the register. So the branch requires the use of your ALU output to determine the next instruction address, which comes either from the ALU, that means where the program counter and your branch offsets are summed from an adder that increments your 4 bytes, that increments the 4 bytes. So the thick line interconnecting the functional units represent these buses here. All these thick line represent the buses here, and which consist of your multiple signals. These buses consist of the multiple signals. So how those, let us see those buses, the thick lines, they are having the multiple signals here. So in this diagram shows the data path from this overview part by adding the extra elements, that is your logical elements, we call the multiplexers, to find the sources from different sources. So this with the 3 required multiplexers, adding to our previous the diagram, so as well as the control lines for the major functional units, we are adding the control unit to do the major functional unit. What are the major functional unit? One is your registers, another one is the ALU and your memory. So these are the functional units, right? So a control unit which has the instruction as an input, it will take the instruction as an input to this control unit, right? And this input is used to determine how to set the control lines for the functional units and 2 of the multiplexers. This multiplexer and these multiplexers, right? And the third multiplexer, which is using here, the third multiplexer, which determines which program. This is 1, 2, and the third multiplexer, which is used to determine the PC plus 4 or the branch destination address is written into your program counter. And it's set based on the 0 output of the arithmetic logic unit, which is used to perform the comparison of a branch instruction. So the regularity and simplicity of the millions of instruction per second instruction set means that a simple decoding process can be used to determine how to set the control lines. So let us just examine inside this the CPU part. The top this multiplexer, the top multiplexer that control what value replace the PC that is your PC plus your 4 or the branch destination address So the multiplexer is controlled by the gate called your AND gate. This multiplexer controlled by your AND gate. Together, the 0 output of your arithmetic and logic unit. The 0 output of your arithmetic and logic unit given as an input to your AND gate, and another one is your branch instruction, which is given the branch instruction given as an input to your control unit. From there, the branch is selected, and that branch is given as an input to AND. The output of your AND will control this multiplexer, whether to go to the next instruction or follow the same instruction. If it says go to the next instruction, then it will add PC plus 4 so that the next instruction will be given. That next instruction signal address next instruction address is forwarded to your instruction memory. So next instruction will be fetched. From that next instruction, the next registers will be identified, and if any immediate value is there, that immediate value is given as an input to your ALU. If there is no immediate value, then your operands will be from your register file only, identified as R2, your R3, and destination is in R1. So in R1, this data will come and store. From R2 and R3, whatever the operands are there, those operand 1 will be given as an input to ALU. Operand 2 will also given as an input to your ALU, and that it performs. Right? So in this case, how this is multiplexer 1 is controlled means it's controlled by your AND. For this AND, one input is from your 0 output. I mean the 0, that is you find the 0 result that we discussed in our previous class, right? So then the control signals that indicates that the instruction is branch here. So the middle multiplexer here, this part, the middle multiplexer, what is the job of this multiplexer? Okay, so this middle multiplexer whose output returns to the register file, the output of this multiplexer is given as an input to your register file, or we say returns to your register file. Correct? So what it means? So this returns to your register file means is used to steer the output of your arithmetic and logic unit. So in the case of an arithmetic logic instruction, or the output of your data memory, the output of your the data memory. So in the case of your load, so for writing into the register file, it is the output is defined into two ways. One is the output of the data memory, or output of your arithmetic and logic instruction. Okay. So finally, the bottom multiplexer, the job of this bottom multiplexer is it is taking the input, one input from your register file, okay, and another input from your immediate value in your instruction. Okay. So from this immediate value, it can select whether the operand is from register or the operand is from your immediate. So that will be selected, and it gives the output of multiplexer given as an input to your ALU. So this bottom multiplexer is used to determine whether the second ALU input is from the register or from the offset field of your instruction. So the added control lines are straightforward and determine the operation performed at the ALU, whether the data memory should read or write, and whether the register should perform a write operation. So the control lines are shown here, all these control lines. These are in color to make them easier to see and understand. These control signals are going for what. If you see this control signal carefully, it covers the branch, whether the branches are like branch equal or greater than, or jump conditional branch, or it covers the register write or memory write operations. Register write or memory write operations, right? So this is the overview of the implementation. We are going to talk about each and every unit in detail, how the data is going to be processed from one unit to the another unit, right? So before going to design and discuss every part of this about instruction program counter, about instruction memory, registers, and the data memories, okay, we consider the data path elements. So we consider the logic design conventions. So what are the logic design conventions are used to implement this MIPS means the data path elements in the MIPS implementation, which consist of two different logic elements. What are those? The elements that operate on data values is one, and the elements that contain the state. One is the elements that operate on data values. Another one is elements that contain the state. So what is the first element? The elements that operate on data values. Okay, that means the elements that operate on these data values are, we call them as your combinational elements. Combinational elements, which means that their output depends only on the current inputs. This combinational, the element outputs depends upon the current inputs only. If the current inputs are same, the output is same. Output will not be changed. Okay. So given the same input, a combinational element always produce the same output, right? But other elements, the example for this combinational elements we call such as your adder, multiplexer, or your shifter, that gives the outputs depends only on your current inputs. That means if you write the operation like your R1 is equal to your R2 plus your R3, and if I give the operand values that R2 is always equal to 2 and suppose R3 input is suppose 3, then the result is 2 plus 3. So if you execute this in n number of times, it will the same output. So the output of these combinational elements, gives the current, the output of this one depends upon the current input. If any of these inputs suppose change, R2 is 3, R4 is 3, then the output change. If there is no change in the combinational elements, then there is no change in the what you call the output at the destination. And other elements in the design are not combinational. The other elements in the design are not combinational, but instead they maintain or they contain certain states. They contain certain states. So that we call the sequential elements. Sequential elements. So if you take any memory location, suppose if array is there, then the elements are going to stored in the array like 1, 2, 3, 4, 5. So it is giving the sequence starting from 0, address 1, 2, 3, 4. So it is a sequential element. So such as your memory and the registers contain the state information. So register contain the state information. Which registers? We call the address registers. And their output that depends on their input, that is the data value and your clock. So these state elements has at least two inputs and one output. So what are those inputs? The required inputs are the data values to be written into the element and the clock. Data value and your clock. Why clock? At what time the data is modified. To see that one, to maintain that state, the state elements consist of two parts, data value as well as the clock. So which determines when the data value is written. So the output from the state element that provides the value that was written in an earlier clock cycle. So this clock determines the order of events within a gate and defines when signals can be converted to data to be read or written to a processor component. So what are the processor component? The processor components may be register or your memory. Register or your memory. So a state element has at least two input and one output as said. Okay. So and the required inputs, as said, data value and your control, right? So, for example, to maintain this, the earlier clock cycle part, okay, uh, the output from a state element that provides the value that was written in the earlier clock cycle, as said. So, for example, one of the logical simplest state element is we call the D type D type flip flop. D type flip flop. So D type flip flop means this type. It takes two inputs and gives one output. One input is your data input, another one is clock input, and the output from this state element that provides the value that was written in earlier clock cycle that gives your C time. So, which has exactly these two inputs like a value and a clock and one output. So in addition to flip-flops, our MIPS implementation uses two other types of state elements. One is your memories and registers. Memories and your registers also. So the clock is used to determine when the state element should be written. A state element can be read at any time. So what is this clock methodology then? What this clock methodology is having? So that it is having the state element. So this clock methodology defines when signals can be read and when they can be written. When the signals can read and written. So these state elements are used when the signals are read and when the signals are written. So it is important to specify the timing of read and writes, because if a signal is written at the same time it is read, the value of the read could correspond to the old value, the newly written value, or even some mix of the two. So computer design cannot tolerate such unpredictability. So a clocking methodology is designed to make hardware predictable, to make this hardware predictable. So for simplicity, we will assume and the edge trigger clock. For simplicity, we use this. We call these as your edges. So this is the edge clocking, edge trigger clocking methodology. So an edge triggered clocking methodology means that any value stored in a sequential logic element are updated only on a clock edge. Only on clock edge. So here you can see in this diagram, there is the timing diagram. So the clocks are there. The complete clock cycle is the sequence of, it goes up for your charged signal and 0 for your uncharged signal. So the up, down and your up. So this complete part we call your clock cycle time. Clock cycle time. Goes, the clock cycle is the sequence of it, right? So this, as we are saying, the edge trigger clocking methodology means that any value stored in a sequential logic element. So which is a quick transition from low to high, or we say that vice versa, from low to high or your high to low. So because only state element can store a data value, any collection of combinational logic must have its inputs come from a set of state elements and its output written into a set of state elements. The inputs are values that are written in the previous clock cycle. So whatever the previous clock cycle inputs are there, that will be given as an input to your next clock cycle. So we call these are the rising edges, these are your falling edges, and if you see the clocks are, these two clocks are same, so we call the synchronous clocking. And whereas in this you can find the asynchronous clock time of your C1 and your C2. Okay. So in this, in C1, C2, how you are saying, in C1 the clock edge is high, whereas your C2 it is low. So as said that the inputs are values that were written in a previous clock cycle, while the outputs are values that can be used in a following cycle clock. So here from this diagram you can clearly observe that in a synchronous digital system, suppose the clock determines when element with state will write values into internal storage. So any inputs to a state element, the state element 1 and your state element 2, and gives the combinational logic. So in this combinational logic, it is finding the clock cycle that, so one clock cycle and the second clock cycle for second state element. So the output of your first clock cycle will be given as an input to the next clock cycle. So any input to a state element 1, that must reach a stable value, that is, have reached a value from which they will not changing until after the clock edge. So before the active clock edge cause the state to be updated, so all state elements in this, in our discussion, which we include the memory, are assumed to be the positive edge triggered, that is the change on the rising clock edge. Change on the rising clock edges. Right? So in this, it is clearly showing that there are two state elements, state element 1 and your state element 2. They are surrounding a block of your combinational logic. It is having block of this combinational logic, which operate in a single clock cycle. So all signals must propagate from state element 1 through the combinational logic to your state element 2 in the time of one clock cycle. In the time of your one clock cycle, you can see up, then it goes, then the falling edge, then it goes, and then up edge. Okay, rising edge, then the combinational logic, falling edge, combinational logic, and rising edge. So this up, then down, and then it takes up, it gives the up, then it takes time, and this is your 1, this is 0 bit. So this total gives one clock cycle. So charged one and uncharged one. Charged one and uncharged one. Okay. So the time necessary for the signals to reach state element 2 that defines the length of your clock cycle. So for simplicity, we do not show a write control signal here when a state element is written on every active clock edge. So in contrast, if a state element is not updated on every clock, then an explicit write control signal is required. So both the clock signals and the write control signals are inputs, and the state element is changed only when the write control signal is asserted and a clock edge, these clock edges occurs. So with this, I would like to stop the session here.